Okay, so last time we were looking at 1.1 and we had gotten to not quite the very end, but awfully close. We were working on this table right here, and we had filled in most of this table. We had gotten these last two boxes right here, and then you were supposed to finish those last two boxes on your own. Do those numbers look pretty close to what you found? Excellent. So imagine what's going on here. We have a piece of a curve, and what we've literally done is we've broken it into 4 pieces, and we've taken each of those pieces and we've drawn line segments. So here's my curve. Here are my 4 pieces that we've sort of broken it off into. This is not in any way, shape, or form accurate, but the image is still the right idea. And we've taken this point, and we've drawn a straight line between them, and we found the length of that line segment. We've done the same thing here, and the same thing here, and the same thing here. So that's the picture of what we've done. Is everybody with me? So if we want the length from 0 to 3, and we've got each of these 4 individual lengths, what do? We add them together, exactly. So we take the sum of these 4 very long 6-digit, right, decimal numbers over here, and we add them together. And if we do, we get a number to 4 decimal places then, because we don't want to lose the accuracy, because those last 2 decimal places are going to have a level of inaccuracy in them, so I stopped at 4 decimal places. So the length of this is approximately 3.1673. Okay, does that make sense to everyone? From last time, I know we just kind of jumped right back in there, but now the other part of this question says that we're going to find the length of the curve with n equal 8. So we're going to do this with 8 line segments instead of with 4. So we have this table that looks a little bit bigger. Now parts of this table are exactly the same. We start with 0, and we end with 3. And the darker gray segments, or lines, that I have in the middle here of these rows, those are actually the same from the previous screen. So we have a 0.75 here, a 1.5, and a 2.25. Not only that, but the output values for those are identical as well. So I have this one value, I have 1.322876, have 1.581139, and I have 1.802776, that is a 0, doesn't look much like one. And the value for that 3 was the number 2. But we've taken those segments now and we're going to cut them in half. That's how we get 8 segments instead of 4. So if I take this and I take a look between 0 and 1 and 0.75, what's halfway between those two numbers? .375, yeah. And then I need the number halfway between 0.75 and 1.5. What's that number? 1.125. Okay, now there are at least 2 ways of finding that 1.125. So somebody give me one option. How did you find it? Okay, not. Okay, so you found that the difference between the two is going to be the 0.37, or it's going to be 0.75, and then half of it's 0.375. Yeah. And so you took that 0.375, just like this 0.375 we got here, and you just added it to the number. To the 0.75. So if we do that, we can just take that 1.5 and add 0.375, right? To get the next one? Because all these differences are the same. And we can take the 2.25 and add 0.375. That's one way to do it. Does anybody else do it differently? You could. You could add the 2 numbers that you're surrounding with and divide by 2. So we could add 1.5 and 2.25 and divide by 2. 2 very different ways, not very different, but they are distinctly different ways of doing the same thing. So if we do that, what's between 1.5 and 2.25? Right? And what is between 2.25 and 3? Excellent. Now, for those of you who didn't have your calculator with you last time, I want to run through real quick just how we enter these to find the f of x in your calculator. So that's why I have this other screen open. So if you take your calculator and you put in y equals, you're going to put in the equation that we've got, which is square root of x plus 1. And then if you don't already have it again set up, if you did this last time, you already have this set up, you're going to use the second window, which brings you into the table set feature. And you want to make sure this one that says independent here is on ask. That lets you control what number goes inside of there that you're interested in finding the y value for. And then once you've done that, you can hit second graph, and it takes you into a table. And in this table, you can put in whatever x values you want, and it will give you back out the y values you were looking for. So if you take a look on our table right here, we're interested in a few new values. The first of which is 0.375. The second one is 1.125. Then we have 1.875. And lastly, 2.625.
Can you change the number of decimals that you?
Actually, you can see more decimals. You can't change how wide that column is, but what you can do is this. So let's go up there to 0.375. I want to know this value, but I want it to 6 decimals so that it'll be more accurate. You just go over and highlight on top of it like this. And then on the very bottom, it shows you as many decimals as the screen will contain. And so you can get the full 6 decimals that we want on this problem. So if we go through and we do that on all of these, we can find out that at 0.375, I have 1.172604. And then the next one is 1.457738. I have 1.695582. And the last one is 1.903943. All right, so what I'd like to do is I'd like to talk through how you fill in that last column, but not actually do it, because we've already done it once. We just did it for a much smaller data set, half as big as what we're working with right now. All right, so remember from last time, what we were doing is we're finding distance between the 2 points. There isn't any previous point on the first one, so there's nothing to put into that box. But on the second one, what we would be doing is we would use the previous 2 lines, the 0, 1 for one of our x values, and the 0.375 and 1.172604, and we'd use that with the distance formula. And we'd find the distance between those. And just like we had before as well, all the distances between x values are all the same, right? They're always 0.375. So part of the distance formula is going to stay static. It's going to stay stationary as I work through the other part. All the differences in the y values are going to change. All that's going to be different, and you're going to have to re-enter portions of it each time. But the x value portion is going to stay the same. So as you're entering this into your calculator, you're going to have the first one, for example, is going to look like this. You're going to have that 375 squared. You're going to have that added to, and then the y values for the 2 that you have next would be 1.172604 minus the first y value, which was 1 squared. And each time those 2 y values, 1.17 and 1, one of the numbers at least changes because you're using a different y value for the next value. After you do that, you end up with 8 values down here, and what do you do with those 8 values? You add them, and that will give you the distance, or at least approximation of the length of the curve. I'm going to give you that sum just so you know what it is so we can compare it to the other one. That sum is approximately the length, and the value that you get is 3.1677. So if we compare that 3.1677, the last time it was 3.1673, the only thing that changed was the very last decimal of 4 decimal places, right? So would it be very time effective or practical to make this 16 segments? No, it wouldn't, because it's not changing very much as I increase the number of segments. Does that make sense? All right.